In this lecture, we shall consider the case of a cantilever beam with an uniformly distributed load over the entire span. We shall find the equations for expressing shear force and bending moment and plot the corresponding diagrams. Let's draw a cantilever beam AB of length L with end A fixed and end B free. Let's dimension the length as L meters and show an uniformly distributed load, that is UDL, of value W kilonewton per meter acting downwards over the entire span. Let's also denote an arrow at reference end B pointing towards the left, indicating the distance of the imaginary cross-section from it. The resistive shear force and bending moment values shall be calculated at the imaginary section of the beam, considering the right part created as a free body in static equilibrium. Let's now drop down some projections from points A and B for drawing the shear force and bending moment diagrams. We show the zero value datum lines and name the corresponding diagrams. For clarity of understanding, let's draw only the right part created by virtue of the imaginary section as a free body diagram and label the necessary parameters. The uniformly distributed load of W kilonewton per meter acting over the length of x meters can be taken as an equivalent point load of W times x kilonewtons acting at the center of the rectangular loading area. We hence show the equivalent point load at the center of the span of length x to represent the UDL. The shear force at x can be written as plus W times x kilonewtons, since both the equivalent point load and the shear force at x produce a clockwise couple for which the shear force at x can be assigned a positive sign as per our convention adopted. We also write the range of x for which the shear force equation holds true, that is, x is greater than or equal to 0 and x is less than or equal to L. Let's apply the values of the range of x and plot the shear force diagram. If x equals 0, that is for point B, shear force equals W times 0, which is 0 kilonewtons. And if x equals L, the shear force equals positive W times L kilonewtons. We observe that the power of x in the shear force equation is 1, meaning that the shear force values vary linearly over the length of the beam. Hence, the locus of shear force over the length is an inclined straight line. The uniformly distributed load creates a hogging bending moment at section x. Hence, m at x or bm at x can be written as minus w times x times 1 half x, and that's equal to minus w times x squared over 2. Here too, the bending moment equation is valid for x varying between and including 0 and L. We observe that the power of x in the equation is 2, meaning that the locus of the bending moment values obtained over the length is a parabolic curve. Applying the limits of x, we find that the bending moment at the free end B is 0 and at the fixed end, that is for x equal to L, is minus w times L squared over 2. It now remains to see if the parabolic curve to be drawn between these two positions is a maxima curve or a minima curve. For this, we check the sign of the double derivative of the bending moment equation with respect to the variable x. We find that the double derivative is negative in sign, meaning that the locus is a maxima curve. We hence draw this approximately between the two positions and name the curve as parabolic. We hence have the maximum shear force as W times L and the maximum bending moment as W times L squared over 2 without much consideration to the sign, both developed at the fixed support. These shall later be used to find the induced maximum shear stress and maximum bending stress respectively for analyzing the failure characteristics of the beam material. In the next lecture, we shall consider a cantilever beam with the point load at the tip combined with the uniformly distributed load acting over the entire length.